So last day, Nathan, I tried to convince you of this strange idea that the speed of light was a constant, and because of that, if you used light as a timing device, you ended up with time shifting. We did the spaceship experiment. What we want to look at today are the actual mathematical equations. So along came Albert Einstein, and he offered the following explanation. He began with two postulates, two theories. He said, look, this is what I believe. Here was the first postulate of the relativity principle. He said, if two frames of reference move with constant velocity relative to each other, then the laws of physics will be the same in both frames of reference. Rather, I'm going to say that again because it was important and you were looking over away. If two frames of reference move with constant velocity relative to each other, then the laws of physics will be the same in both frames of reference. That's hugely important to all of your lives. That's why, for example, if you pour a cup of coffee while on a jet plane, even though the jet plane is traveling forwards at 700 kilometers an hour, the coffee doesn't go shooting back at you and land in your lap, because the coffee is also traveling at the same velocity relative to the plane, and therefore the laws of physics will be the same. Oh, and you are also traveling at the same relative velocity as the plane. The laws of physics will be the same. What it really means, the concept of the consequence of that then, Andrew, is you can't tell if you're moving. If you look, by the way, are we moving right now or standing still?
No, we're moving.
What, did you hear Matt? Standing still. Oh no, what are we?
We're moving.
How are we moving?
The Earth's rotation.
Can we tell? No. Why? Because relative to the Earth, we are moving at exactly the same velocity as the Earth, and therefore the laws of physics are the same here. There is no way, and this was very revolutionary because at the time people thought there's got to be some way we can say you're at rest, and Einstein said, no, you can't. That's why he called it relativity. He said all motion is relative. All motion is relative. You can try this. Try playing catch in a car. If in the back seat, not while you're driving. Sorry, you're teenagers and might misunderstand that. So a couple little illustrations there. I'd like you to use your imagination. Don't turn the page just yet. Let's suppose we had a van that was made out of glass so you could see through it. In the van, if I throw the ball straight up and it comes straight down, that's what I would see. What would an observer who was standing by the side of the road see the ball travel like if the van was moving forward? How would that look to the observer? Would they see this? Well, there would be a horizontal motion as well. What would they see, do you think? I think they would see something like this. Let's suppose that we drop the ball, or that we throw it up. They would see the ball going up, but also moving forward, and then the ball coming down. They would see this sideways component to the motion, because the person in the car thinks they're standing still, but the person outside of the car, Jordan, thinks, no, the car's moving. Does that make sense? So sketch that. To sketch what the path of the ball thrown in the van would look like to an observer standing on the road looking into the van as it passes. I think something like that. And that may not sound profound, but what we're going to do then, Riley, is we're going to ask, what if instead of a car, we're going to make it a spaceship? And what if instead of a ball, we're going to make it a beam of light? And we're going to ask, what would the path of the beam of light look like to somebody who was on a planet with a powerful telescope watching the spaceship go by? This was Einstein's little thought experiment. Here was his second postulate, by the way. He said the speed of light in space is the same for any observer, no matter what the velocity of the observer's frame of reference is, and no matter what the velocity of the source of the light is. Say what? The speed of light is constant. I'll even tell you what it is. It's 3 times 10 to the 8th meters per second. It's actually 2.9978. You know what? To 4 sig figs, it's 3, and that's good enough for us. What's the speed of light? What word did I write next to it? constant. Traditionally, because of that, we use the letter lowercase c for the speed of light. That is reserved for the speed of light. That's the c in the E equals mc squared Einstein's equation that you may have heard about. So let's talk about time dilation. Turns out that your time is not equal to my time necessarily. Your time is only equal to my time if our relative velocities are identical, if we are at rest relative to each other. Note, the word dilate means to make wider or larger. According to Einstein's special theory of relativity, a clock that is moving will run slower. You guys have seen how I love to have my watch matched to the second of the tone. Is it moving? I've just slowed my watch down. Probably not until about 15 decimal places, because I wasn't moving very fast. But I'm telling you, if we had a really accurate measuring device, you would notice it. A little weird. This stretching of time by a moving object is called time dilation. dilation. Well, that word right there, time dilation in the title. And there is an equation to calculate it, and to prove the equation, you need Math 8, which is kind of cool. So here is our thought experiment. We're going to have our transparent spaceship, and what we're going to have is we're going to flash a beam of light up and back down on a mirror. At the same time, we're going to have the spaceship be traveling a speed v. Okay? Now, light doesn't accelerate, so our equation that we're going to use for our distance v and t is going to be that. We don't need to worry about the half a t squared portion of it. You okay with me, Elijah? What we're going to try and come up with are mathematical expressions for distances based on each frame of reference, based on the person inside the spaceship and based on the person outside the spaceship. So the person inside the spaceship, if they measured how long it takes the light to go from here to here, that distance would be the speed of light times t. And you know what? We're going to call that t our original time at rest as far as the person is concerned. So we're going to call that t0, t initial, t start, time start. You with me so far? Physics 11, but at the speed of light. Next page. And if you were in that spaceship and you were superhumanly quick on your stopwatch, you could measure that time t. It's a finite time. I think we could crunch the numbers, but whenever I look at Matt, who's sitting right here, for example, I'm technically actually looking back in time because it takes the light about 2/billionths of a second to get to my eyes. So if you vanish in the next 2/billionths of a second, I won't know right away. There will be a split second when I still think you're there, when you're actually not. It does take time for the light to travel. Okay? Is it possible that in two different frames of reference at different speeds, identical clocks might run differently and that time might pass differently? In fact, this is one of the predictions of Einstein's special theory of relativity. So here's our picture. Figure 15.6 illustrates an observer inside an imaginary, custom-made, glass-walled spaceship. It's a thought experiment. Made especially so that an outside observer, let's say somebody on a planet with a really powerful telescope can watch an experiment done by an inside observer. The inside observer is watching an event consisting of an imaginary oscillating light beam. The light beam is going bing, 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 back and forth. We're going to look at just one trip. And we've said that this distance this way is velocity times time, speed of light. The oscillating light beam acts like a clock. The beam goes from the source up to mirror A and back to mirror B. The inside observer measures the time for the light to travel from A to B, and he finds that that time on his stopwatch is, we're going to call it T0. And since distance is speed times time, the distance that the inside observer sees the light beam travel is d equals speed times time. So far, so good? But now it gets a little strange. Stay on your page. Figure 15.7 illustrates what an observer in a different frame of reference sees. The outside observer is not moving at speed v. So let's go back to this picture. The outside observer is not moving at speed v. To him, he feels he's standing still. The spaceship is moving forward at speed v. And so he sees the spaceship going by at a speed relative to him, where the observer sees the light travel straight down that distance. The person outside the spaceship sees the light travel like that, the same way as that thought experiment, William, when we were playing catch in the van. He sees this distance, speed times time. Now, this time that he sees is not the same as time 0 because the speed of light never changes. He measures this distance, he divides by the speed of light, he gets a different answer. And you get a lovely right angle triangle forming. Turn the page. If we draw a picture, here's what we have. There's the guy in the spaceship, what he sees. He sees a distance from here to here. And that distance, rather than calling it distance, Sean, I'm going to call it speed times time. Okay? The person outside the ship sees two things. With their stopwatch, to them the beam of light looks like that. They know the speed of light is c, but their stopwatch, when they measure it, Elijah, they measure a time t, a different time than the person inside the spaceship measures. So this is a distance. The hypotenuse is a distance. We want to make this a distance as well. Well, this is the speed of the spaceship times time. Tanisha, do you agree with me? All of those are distances. Okay? I know you don't see a d there anywhere, but it's vt, vt, vt. We've agreed all year long. As long as there's no acceleration and light doesn't accelerate and the spaceship's traveling at a constant speed, we're good. You know what that means? I can use Math 8 Pythagoras to prove relativity. I can go a squared plus b squared equals c squared. I can go that squared plus that squared equals that squared. Yes? Then what did I write for step 2? What did I say we needed to do? Let's get the CTO squared by itself. Let's minus the VT squared over. So I'm going to have this. CT0 all squared equals CT squared minus VT squared. What did I say for step 3?
Distribute the power.
Except as I did this, realized I didn't leave you guys enough room, so we're going to distribute powers, but we're going to do it on this line up here. It's going to be c squared t0 squared equals c squared t squared minus v squared t squared, right? Send the exponent through, McKenna. If you have something in brackets all squared, it's each thing squared. What did I write for step 4?
Factor out t squared.
So on the right-hand side, can you see there's a t squared in both terms? Why, that's a greatest common factor, a GCF, as it were. So I can rewrite this as c squared t0 squared equals, I can factor out a t squared, and I get c squared minus v squared. And I know all these letters rhyme, and it's tough to keep track of, but can you see the algebra okay? What did I say for step 5?
Divide both sides by c squared.
So we're going to go like this. Divide by c squared. And then we're going to get clever. Don't write this next bit down. Instead of dividing by c squared right there, what we're actually going to do is we're going to divide everything in the bracket by c squared. We're going to go divide by c squared, divide by c squared. We're going to multiply that c squared into the bracket. Because I like that t squared where it is. Why did I do that? Yes? What is c squared over c squared?
0.
What's anything divided by itself? I think not 0. 1. And then I have minus v squared over c squared. That looks a little cleaner. And then step 6, yeah, you'll need to turn the page. Isolate t. I want to get not the t0, I want to get the t by itself. How would I get that t by itself? What's the bracket doing to the t mathematically? Timesing, so how will I move it over? But that gives me a t squared. How to get rid of a squared?
Square root.
Notice that we're proving relativity with Pythagoras Math 8, which I think is kind of nerdly cool. You're going to get this. T equals t0 squared, all divided by this bracket. Now I can drop the bracket because it's all in the bottom. And then how do I get rid of a squared?
Square root.
And here's what I'm going to do. Look up for 1 second. I'm going to square root the bottom, but if I square root the top, what is the square root of t0 squared? What happens when I square root a squared? This is the time-dilation equation. This is what Einstein did. He started out, Elijah, with this thought experiment of a transparent spaceship. And he said, well, look, if the speed of lights have to be the same, and if I allow time to change, I can draw a Pythagoras triangle. And we get this in the box. Here we go. Time equals t0 over the square root of 1 minus v squared divided by c squared. Where capital T, where lowercase t, the left-hand side, this tells you the dilated time, the stretched time, where t0 is the time if everything was at rest, or if you just decide that that's going to be your at rest, because William, we said actually you can't prove that anything is at rest in the universe. In fact, nothing is at rest in the universe. But whatever you decide, Andrew, to be your, here's our 0 point. Speed that you're traveling at. speed of light, which is 3 times 10 to the 8th. As an example, let's use this, example 1. By how much is time expanded or slowed down from a fixed observer's point of view, let's think, compared to the Earth? If a spaceship is moving at 1/2 the speed of light, if the v is 0.5 c. Can you put it face down in the appropriate box? Well, let's write down our new time dilation equation. Okay. T0 is just, we're just going to leave it as T0. We're not going to plug a time in. We just want a comparison. What's V? How fast is this spaceship traveling? 0.5 c, which is pretty fast. So we're going to leave this as T0 over big square root 1 minus, and for the V, I'm going to put 0.5 c all squared. Riley, you okay with that substitution, right? The squared is outside the v, so I said I'll replace the v with a 0.5 c all squared. And now I'm going to put the exponent onto both of those. I'm going to tidy this up. So I'm going to say this is T0 all over big square root 1 minus, what's 0.5 squared? What's 0.5 squared? Calculator or in your head, I don't care, but no, silence is not acceptable. 0.25? What's c squared? I think just c squared over c squared. Andrew, what happens to the c squared on the top and the c squared on the bottom? It becomes a 1, right? Yoink. So I get T0 all over the square root of 1 minus 0.25. Hey, what is 1 take away 0.25? This is T0 all over the square root of 0.75. What is the square root of 0.75?
0.87.
Now, where is that square root of 0.75? On the bottom or on the top of my fraction here? On the bottom. So don't write this down. I want you to realize this is really 1 over the square root of 0.75 times T0. And what I'm trying to do is find by what factor T0 is stretched by. So can you actually on your calculator go 1 divided by 0.75? Because that's going to be my dilation factor. Sorry, 1 divided by the square root of 0.75?
1.15.
1 divided by the square root of 0.75. 1.15. So putting that into math terms, time will be 15% slower. See where the 15% came from, the 0.15? If you're going at half the speed of light, compared to the Earth, you will age 15% slower than the Earth. Time will take 15% longer for you relative to the Earth. You got to go pretty fast. By the way, if you try putting in a number right here, like 30 meters per second, see, what happens is this number down here is so big that you get a small number divided by a really big number. What is a small number divided by a really big number? Really small, you get 1 minus almost 0. You get almost 1. And what's the square root of 1? 1. What's the square root of almost 1? Almost 1. You basically get no change. You're dividing by 1, roughly. Example 2. Imagine your age is 30 years, and that you have a daughter who is 6 years. The abbreviation for years, by the way, is not Y. Y is yards. The abbreviation for years is A annually. So imagine that your age is 30 years, and that you have a daughter who is 6 years old. You leave on a spaceship in the year 2000, and you travel at 99% of the speed of light, 0.99 c. for 5 years as measured by you in the spaceship. How much time will have elapsed when you return? And how old will your daughter be when you get back? Let's find out. Sorry. T equals T0 all over the square root of 1 minus v squared over c squared. This time, I actually told you how much time elapsed. What's T0? How much time elapsed on the spaceship? How fast is the spaceship traveling? So we'll put 0.99 c all squared divided by c squared. That's going to be 5 divided by big square root 1 minus, it's going to be 0.99 squared c squared over c squared. Hey AJ, what happens to the c squareds? Five divided by the square root of 1 minus 0.99 squared. Okay. Now I'm not trying to find a ratio like in the previous one where I said, how does time compare to T0? Now I actually want to know, okay, 5 years on the spaceship is the same as how many years back home? I'm going to go 1 minus 0.99 squared. I'm going to go square root of that. 5 divided by that answer. What'd you get? By the way, you need to know how to type this, so you may as well practice this on your calculator, boys and girls. It's good practice for your final exam. Thought you said this wasn't going to be on your final. Yeah, relativity isn't going to be, but you need to know how to type stuff like this in.
35.43.
Holy smokes. $35.4 years. How old were you when you left? What does the question say? 30. How many years were you gone as far as you know? 5. So how old are you when you get back? 35. As far as you know. How old was your daughter when you left?
3.
How many years of time elapsed for her?
35.
How old is she when you get back? Your daughter.
42.
Doesn't violate the laws of physics. In fact, physics says that's what will happen. Your daughter will be older than you. Okay? This is going to, if we find a way to travel in space, and we can approach these relativistic speeds, William, they're going to be somewhat one-way tickets. It's going to be, okay, you want to go on a trip for 10 years at 99% the speed of light? Fine, understand, probably 200 years will have passed on the Earth. Everyone that you knew will be dead. Okay? And some people will like that. Like some people will, I want to break ties with everybody and I want to go. Some people, that's going to be a big issue. If you got a wife and kids and husband and kids and you got family, you're saying bye to them. Unless you take them with you, you're saying bye to them all. There's some staggering implications, both societally and economically. Hey, why don't you invest $1,000 and go on a 10-year relativistic trip, and you come back and that $1,000, because maybe 600 years have passed on the Earth, is now worth several billion dollars? Ooh, I don't know. Or what if something goes wrong while you're gone? And the Earth that you come back to has, well, even think about the changes in the past 50 years. What if you missed all of those technological and societal changes and you arrive back? You'd be a fish out of water. So the whole space travel, Star Trek, there are some very serious implications if we can ever get that fast. It gets weirder. How can it get weirder? You just told me that my kid's older than me. Oh, it gets weirder. Einstein's theories, Jordan, show that not only does time dilate, get bigger, but as you approach the speed of light, length contracts, gets smaller. Without going into the mathematical detail, we're simply going to say this. If an object is standing still, is measured to be L0, the theory of relativity predicts that the object's length L, when it's moving at speed v, will be measured to be that. You'll notice the same square root factor appears, 1 minus v squared over c squared, except it's no longer in the bottom of the fraction, it's in the top of the fraction. It's on top. Example 3. Let's suppose a meter stick moved past you at 99.5% of the speed of light, 0.995% of the speed of light. How long would it appear to be to you, even though you knew it was a meter stick? How long would it appear to you? The length that you would see is going to be the original length standing still times 1 minus v squared over c squared. What's the length of the meter stick when it's standing still? It's meant to be really obvious.
1 meter.
1. Square root of 1 minus, and we're going to go 0.995 times c all squared divided by c squared. Can I drop the 1 in front, please? That's not going to make a difference, yes? It's going to be the square root of 1 minus 0.995 squared c squared over c squared. What happens to the c squareds? So on your calculator, go 1, take away 0.995 squared, get an answer, square root. How long would that meter stick appear to an observer who felt they were standing still?
Zero point 0.099.
10 centimeters. 90% length contraction. Okay? This is the universe that we live in. By the way, don't write this down. How fast does light travel at?
2 times 10 to the power of 8.
The speed of light. You know what? Let's put the speed of light into that equation. What is c squared divided by c squared?
1.
What is 1 take away 1?
0.
What's the square root of 0?
0.
What's wrong with that?
10 divided by 0.
This is why we believe that we can't ever get, one of the reasons we believe we can't ever get to the speed of light. But here's what else this means. So when you see the light from distant stars and it's taken years or decades or centuries or millennia to get to us, that's relative to us. If you're traveling at the speed of light, how much time has elapsed? None. As far as the light is concerned, it left got here. There was no travel time for the light as far as the light is concerned. This is the universe that we live in. Only because we're so used to thinking of ourselves standing still. And even though you guys have learned some astronomy, when I said, are we moving? Most of you, your first inclination, well, yeah, we're standing still. Oh, I guess we are moving. We just have our own frame of reference. We've decided that we're the 0 point, but understand, as far as light's concerned, it's traveling everywhere instantly. Weird. Cool.
Where's the what part?
Pardon me?
Weird or what?
Yeah, weird or what? I just think totally cool. So if you want to try some of this, this will be your final assignment of the year. 1 and number 2. The answers are attached.